So welcome everyone to the fifth seminar in the ReMO seminar series. And tonight's presentation will be given by Wang from Dalhousie. He's a PhD student of Katja Fennel, and he will talk about biogeochemical Argo data and the contributions of small particles to carbon flux in the subpolar North Atlantic. So welcome, Bin, and we're all looking forward to your presentation. The screen is yours.
Thank you. I'm Bin Wang. So today I'm going to talk about how I use the BGC Argo flow data to derive the reionization rate and thinking velocity of the POC. And then I use these parameters to calculate the vertical carbon flux due to the different mechanisms. So briefly, our results show that the gravitational sinking flux of the large POC is the most important mechanism. But we also find that at the same time, the small POC can also make a significant contribution to the vertical carbon flux in the subpolar North Atlantic. And now this work has been accepted by the New Knowledge and Oceanography recently, and it's published in this morning. So in the next presentation, I will present more details about this work. Okay, so first, as we all know that the biological carbon pumps include the production of the organic carbon in the surface ocean through the photosynthesis, and the subsequent transport of this organic carbon from the surface to the deep ocean. During this vertical transport, this downward carbon flux will be attenuated with the depth due to the different processes, such as the reionization, the fragmentation, and extraction. So as a result, the most of this organic carbon will be reionized into the inorganic carbon and be recirculated back to the surface ocean. Only a small fraction of the organic carbon can survive this respiration to reach the deep ocean and be sequestered in the deep ocean. So the net effect of this process is to remove the carbon from the surface and can maintain the ocean's uptake of CO2 from the atmosphere. So the biological carbon pump can control the atmospheric CO2 levels, and it's important from an economic standpoint. However, the current estimate of this very important carbon flux still have large uncertainties, and here we have one example. So this figure shows the global estimate of the vertical carbon flux at the base of the euphotic zone, which is also referred to as the carbon export flux from the several previous studies which use a different method. And we can see from this figure that this estimate vary a lot from about 4 to more than 10 petagram carbon every year. In addition, the potential of this vertical carbon flux to reach the deep ocean and to be sequestered there is even more uncertain. Some studies believe that the more fraction of this organic carbon can reach the deep ocean in the low latitude regions, and this fraction will decrease to the higher latitude regions. But other studies also have an opposite global pattern. We believe that this fraction should be higher in high latitude regions and lower in the low latitude regions. There are many different reasons behind these large uncertainties, but one of the most important reasons is the insufficient observations. So this indicates that the additional observations is very important. In the recent years, the BGC Argo flow data has provided us a large number of profiling observations of the key biogeochemical process in the high resolutions in the global ocean. So, and these observations also contain a wealth of information about the biological carbon pump. So in this study, we will try to use this new type of observation to calculate the vertical carbon flux due to the different mechanisms. For this purpose, we will first integrate the POC concentration from the base of the mesopelagic zone, which is defined as 900 meters here, to any depth above. And we use the subscript to represent two POC classes, where we use the S is used to represent the small slow sinking POC, and L is to represent the large fast sinking POC. So the vertical integration of the small POC can be supplied by the vertical carbon flux from the upper layers and can be reduced due to the remionization. In addition, it can be also supplied by the fragmentation of the large POC into the small POC. So here we assume that the vertical if we assume that there is no flux of small POC out of the mesopelagic zone, the vertical integration of the temporal evolution of the small POC inventory can be represented by this partial derivative equation, where the remionization and the fragmentation is assumed to follow the first order kinetics. And here, the parameters IS and DL represent the carbon specific remionization rate of small POC and the fragmentation rate of the large POC. So this partial derivative equation can be resolved analytically to calculate the vertical carbon flux of small POC from the upper layers, if we assume that this flux is a constant between two consecutive sampling steps, which is represented by the delta T in this equation, and is typically from 1 day to 10 days for the BGC algo flow data. At the same time, we can also calculate the gravitational sinking flux of the small and large POC based on their definitions. So they are the product of the POC concentration and their corresponding sinking velocities. And then we can attribute the vertical carbon flux of small POC apart from gravitational setting to other mechanisms, such as the mixed air pump, the additive subduction pump, and etc. So to calculate this different vertical carbon flux, we have to find the values for this key parameters. They are the carbon-specific remionization rate of the small POC, the fragmentation rate of the large POC, and the sinking velocity of two POC classes. So in this study, we will calculate these parameter values, and we apply these equations to 3 BGC algo flows in the subpolar North Atlantic, which measure the both action and backscattering coefficient, where the backscattering coefficient is a proxy measurement of the POC concentration. And from this figure, we can see that the BGC algo flows can move a long distance over the period of their deployment. They can sample waters with the different physics and biological properties, and therefore their vertical carbon flux and the associated parameter values can be very different. So here I take one float X example. This float is represented by the red line in this figure, and it's deployed for about 4 years. So here it shows the vertical distribution of the temperature, the oxygen concentration, and the AOU, which is an abbreviation for the absolute oxygen utility. So we can see that this float moves from the emergent state with the relatively warm water and low oxygen concentration to the center of the nebulous state with the relatively cold waters and high oxygen concentration. So to minimize this effect, we will divide each float into several 1-year segments, and we will calculate the vertical carbon flux and the associated parameter values for each float segment. Yeah, so this is the figure shows each float segment, and the green lines that we didn't use their data because of they have the drift. The BGC algo flow data can also allow us to separate the small and large POC concentrations by smoothing their raw BVP profile. As shown in this figure, the smoother baseline, which is represented by this black line, and the residual spike signals, which is represented by the green bars, can then be used to estimate the small and large POC concentrations based on their entropy relationship with the POC concentration. And after we have the POC concentration, we can relate the declines of oxygen with the time to the reionization of small and large POC, but neglecting the physical advection and diffusion. And in practice, we only use observation to know the mixed layer depth to remove the influence from the LC exchange. And we use the ALU instead rather than the absolute oxygen concentrations to account for the influence from the change of temperature and salinity. And then we will test a wide range of parameter values for these two reionization rates by reporting their root mean square errors between the predicted and observed data ALU. So here is the distribution of the root mean square errors in the space of the reionization rate. The X and the Y axis represents the reionization rate of the small and the large POC. So the optimal parameter values can be obtained by minimizing this root mean square error, which is represented by the black dot in this figure. And in this study, to account for the uncertainties, so we define the possible values within these black circles, where the corresponding root mean square error is no larger than the minimum root mean square error by 0.1 million more oxygen per cubic meter. So now we have the reionization rate, and then for other parameters, we will look at the vertical profiles of the POC concentration. We assume that the sinking velocity is a constant, and so the mean vertical profile of the large POC can be represented by this exponential equation. And the shape of this equation is only determined by the reionization length scale, which is a ratio between the sinking velocity and the net attenuation rate. For the large POC, this net attenuation rate is the sum of the reionization and the fragmentation. So we can fit the mean vertical profile to this exponential equation to find a value for their reionization length scale, which, for example, is about 250 meters in this float segment. We can also do this calculation for the small POC, but then we find that the reionization length scale of the small POC is increasing with the depth. Given that we assume a constant sinking velocity, this can be only explained by the decreased attenuation rate of the small POC with the depth, which consists of the reionization as the sink of the small POC and the fragmentation of large POC as the source of the small POC. So here's the question: why the small POC behaves like this? Why they behave unlike the large POC? The reason is because the reionization tends to remove small POC preferentially at a shallow depth. So we can see with the depth increase, the large POC will become relatively more abundant than the small POC. And the result is the fragmentation of large POC into the small POC will become relatively more important and can slow down the net attenuation rate of the small POC more efficiently. So after a suite of derivation, we will have such equations to describe the relationship between the reionization length scale of the small POC and the ratios between the two POC classes. So this is a linear equation, and we can do a regression analysis between these two terms to find the values for the regression slope and the regression intercept. And because we already know the reionization rate of the small POC by relating the declines of oxygen to the POC concentration, we can easily know the value of the sinking velocity of small POC and then the fragmentation rate of the large POC. We can also calculate the sinking velocity of the large POC based on this equation, which is the definition of the reionization length scale of the large POC. So now we have all parameters ready, and next we can use these parameter values and these equations to calculate the vertical carbon flux due to the different mechanisms And here is the result at 100 and 600 meters for each flux segment. So from the left to the right columns, they are the total vertical carbon flux of the small and large POC, the gravitational sinking flux of the large POC, the gravitational sinking flux of small POC, the vertical carbon flux of small POC due to other mechanisms, such as the mixed layer pump, the added subduction pump, and etc. And finally, we also have the fragmentation flux. I would also like to clarify that the fragmentation is not considered when we calculate the total vertical carbon flux. So from this figure, we can see that the gravitational sinking flux of large POC is the most important mechanism. At 100 meters, it can account for more than 50% except one flow segment, except this. And at 600 meters, its relative contribution have increased to more than 70%. This also suggests that the gravitational sinking flux of the large POC is the most efficient pathway to sequester the carbon in the deep ocean. At the same time, we can also see that the small POC can also make a significant contribution to the vertical carbon flux by the gravitational setting and other mechanisms. And we can also see that in some flow segments, the fragmentation flux can be as important as the gravitational setting and other mechanisms. This suggests that the fragmentation can be also an important source of the small POC within the mesopelagic zone. Actually, there are previous studies to calculate the vertical carbon flux based on the BGC Argo flow, but they didn't consider the remineralization and fragmentation explicitly in their calculation. So their results should be interpreted as a net flux of these processes. And here I will show how important of considering these two processes to the estimate of the vertical carbon flux of the small POC. So let's first neglect the fragmentation, and then the resulting vertical carbon flux of small POC will be much higher because we attributed the contribution from the fragmentation to the vertical carbon flux from this six. And if we further neglect the remineralization, this equation will be simplified into this form, which has been used in the previous study. And this equation implies that the vertical carbon flux of the small POC from the upper layer is equivalent to the net change of small POC inventory. So as a result, under this assumption, we can see that the annual average of vertical carbon flux will become close to zero and far from what we estimate when we consider the remineralization and fragmentation. This makes sense to me because the net change of the small POC inventory should be pretty small in the annual time scales, and because and this indicates that most of the POC has been refined within the mesopelagic zone. So finally, here is the summary of the main conclusions of this study. By using the BGC Argo flow data to derive the parameter values and the vertical carbon flux due to different mechanisms, we find that the gravitational sinking flux of large POC is the most important mechanism. But at the same time, we also find that the small POC can supplement the vertical carbon flux significantly in the subpolar North Atlantic. We also find that the fragmentation can be an important source of the small POC within the mesopelagic zone. So that's it. Thank you very much.
Thank you very much, Bin, for this very interesting insight into the vertical carbon flux due to small particles. I'll stop recording now, or pause the recording now.